So today we are going to solve the revision worksheet for fluids. So here in the first question, it is about the density, and here you guys can see a student is measuring the mass of two cubes, and mass of both the cubes are same, but at the same time the dimensions, the sides are different. For the first cube it's only about x, and for the second cube it's about 1.5 times x. So you guys know the equation for density. Density is mass over volume, or mass per unit volume. So we can write the density equation for both the cubes. For the cube with side 1.5 times x, so we are taking it as larger cube. So this is density of the larger cube. So rho L is equal to mass. Mass is measured as 50 gram. We are not going to convert this to kilogram anyway, because this is going to cancel when we are taking the ratio. Okay, so 50 over the volume of the cube. So volume of the cube, you guys know, the side cube of the sides. So if we have a cube like this, so if its sides are equal to x, then the volume will be equal to x cube. So here for the larger cube, the sides are equal to 1.5 times x. So we are taking as 1.5 times x cube. So rho L is equal to 50 over 1.5 times x whole cube. So for the smaller cube, we can write 50 over mass over volume. Volume is equal to x cube. So now we are going to take the ratio, which is rho L over rho S. Then you will get 50 over 1.5 x cube over 50 over x cube. So you guys can cancel this 50. So now we get x cube over 1.5 x cube. So which is equal to, so we can cancel this s cube and s cube. Then we get 1 over 1.5 cube. So rho L over rho S is equal to 1 over 1.5 cube. The value is equal to 0.30, or somewhat around 0.29. So we are taking it as 0.30. So rho L is equal to 0.30 times rho S. So this is the ratio between the density of the larger cube and the smaller cube. So this will be option D. So the second question, a sample of seawater is collected using a beaker. The sample contains some particles of sand which settles at the bottom of the beaker. Which of the following would result in a decrease in the time taken for the sand to settle? So decrease in the time taken means it will decrease the velocity of the sand particle which is falling down. So here you can see the first option is smaller particles of sand. Whenever the smaller particles of sand is there, then the downward force will be small. So it is actually resulting in increasing the time taken to settle down. So this one is wrong. So in the second case, lower temperature, you guys know that the relationship between temperature and viscosity, the temperature in liquid, the temperature is inversely proportional to viscosity. So whenever the temperature decreases, viscosity increases. So if you guys look at the equation which is given by Stokes' law, so the dragging force is equal to 6 pi eta RV, 6 pi eta RV. So if you write an equation for velocity, then it will be like dragging force over 6 pi eta R. So here you guys can see this viscosity. Whenever the value of viscosity is decreased, then what happens? The value of velocity, or the particle, the velocity with which the particle moving downward is increased. So here we are actually lowering the temperature, so the viscosity is increasing. So whenever we are increasing the viscosity, then what happens to the velocity? The velocity will decrease. Velocity decrease means the particle take more time to settle down. So this option is also wrong. And the other one, smaller terminal velocity of sand particle. What is terminal velocity? The terminal velocity is the velocity achieved by a falling particle which is in a fluid, and this terminal velocity will be achieved when the upward force is balanced by the downward force. So this is also the velocity of a particle which is falling down when the upward force is equal to downward force. That is terminal velocity. So whenever the terminal velocity is reduced or decreased, then what happens? The particle will take more time to reach the bottom and settle down. So this option is also wrong. And the fourth option you guys can see, lower viscosity of the seawater. So now you guys know whenever the viscosity is small or reduced, then what happens to the velocity? The velocity will be increased. So whenever the velocity increases, the particle will fall down with a greater velocity and it will reach the bottom faster. Then the particle will settle down faster. So D will be the answer. So now we have third question. So here we can see the question is, Stokes law can be used to determine the frictional force on an object which is moving through a fluid. To which the following would Stokes law best apply? So a large sphere moving quickly through a fluid. We said that whenever the motion is quick, then the flow will not be laminar flow. So it will not be the answer. The second one is a large sphere moving slowly through a fluid. So whenever the sphere is large also, then the flow will not be a laminar flow. For the Stokes law, the one of the main condition is that so the flow must be flow of the fluid around the falling sphere, or the sphere that we are using will be laminar flow. So if the flow is not laminar, we are not able to use the Stokes law. So here you can see the third option. So this one will not be the answer. So the third option, a small sphere moving quickly through the fluid. Here the sphere is small, but it is moving quickly. So at that case also, the flow will not be laminar and we can use the Stokes law. In the fourth case, both of them are satisfying the condition for Stokes law. The small sphere, the sphere is small sphere and it is moving slowly through a fluid. Whenever it is moving slowly through a fluid, then the streamlines, if you draw the streamlines for this, the streamlines will be like this. Streamlines will not overlap each other. It will not overlap with each other. So whenever the streamlines does not cross each other, then we can say that the flow is a laminar flow. It's a laminar flow. So there will not be any rotation or curling for the liquid which is flowing. So we can say that the flow is a laminar flow. So this is the right answer. The sphere must be small. At the same time, it must move slowly through the fluid. Now the fourth question. So a student is determined the viscosity of the liquid using a falling ball method. And then the ball is falling with a terminal velocity and the following relation applies. So here you guys know we are considering a ball which is falling down to a fluid. Then what are the forces acting on the fluid? So the forces acting on the fluid will be the upthrust or the upward push which is given by the fluid, and a force which is opposing the motion. So that is actually the dragging force. So what is the drag force? Drag force will be also in the upward direction. So what about the direction of the weight of this sphere which is falling through the liquid, which is equal to mg? It will be in the downward direction. So we know that the terminal velocity is achieved when the upward force is balanced by that downward force, right? So here we can write the equation. The upward forces are the upthrust and viscous drag force. So here we can write the equation like upward force is upthrust plus viscous drag force. I am writing it as F, which is equal to the downward force. Downward force is weight of the body, which is equal to mg. Weight is equal to mg. Okay, now we can rearrange the equation for drag force. Drag force is equal to weight minus upthrust. So this is the equation they are written in this question. So now the density of the liquid is known, and the student used a balance and a digital caliper to make measurements on the ball. Okay, so why are we using a balance? We are using a balance to measure mass, and digital caliper is used to measure the diameter. So here, describe how the student could use her measurements to calculate a value for the drag force acting on the ball. So in the first step, what the student do is, student will measure the mass. So the first step is measure the mass using the balance. So in the second step, we can find the diameter using the calipers. So if we get the diameter, we can half that diameter value, then we will get the radius. So if we know the radius, then we can write the volume, find the volume using the equation 4/3 pi r cube. So if we are able to find out the volume using 4/3 pi r cube, in the next step, we are able to find out the upthrust using the equation rho Vg. So if we know the volume, we can find the value of upthrust using the equation rho Vg. So these are the 4 steps that you guys have to mention. Measure the mass using the balance, measure the diameter using the digital caliper, and find the volume of the ball using the equation V is equal to 4/3 pi r cube. And in the 4th step, we have to find out the upthrust using rho Vg. So V is the volume of the liquid which is displaced. And we know the value of rho, that's already said in the question. We know the value of density of the liquid. And G, you guys know, its value is equal to 9.81. Okay, so if we can measure the weight of the ball and calculate the upthrust, then we are able to find out the drag force. So this is the 4th step you guys have to mention. So the next question is about when falling through a liquid, the ball reached the terminal velocity, the flow of the liquid around the ball was laminar. So they are saying the flow is laminar because they are indicating that it obeys the Stokes law or Stokes equation. So we can use the Stokes equation to find out the answer. Here we have to calculate the terminal velocity of the ball using the equation F is equal to 6 pi eta rv. Okay, so all the quantities are given here. So V is the terminal velocity, and then r here is the radius, and we have to find out the value of eta. The drag force is also given. So we can write the equation for eta like F over 6 pi, which is F over 6 pi eta r. So we know, sorry, rv. So we took eta to the other side, which is equal to rv, F over 6 pi rv. So force is equal to 1.1 times 10 to the power minus 2 over 6 pi r. Radius is equal to 0.50 times 10 to the power minus 2. Then the drag force, we already substituted the value. Terminal velocity is about 5.4 times 10 to the power minus 1. Then you guys will get the answer. So whenever you guys are writing the answer, you have to write the proper unit along with that. So this is Pascal seconds. So you can find the unit from the equation itself. You guys know the equation unit which are using for force is newtons. Then so 6 pi, this is a constant, there is no unit. The radius is measured in meters, and the velocity is meter second raised to minus 1. So it is like Newton over meter square second raised to minus 1, right? So Newton over meter square is force. So you guys know the unit for force, which is Pascal. So we are taking the second raised to minus 1 from denominator to numerator. You guys will get second. So this is the unit for coefficient of viscosity eta, which is equal to Pascal seconds. Now we can move to the 5th question. So here, a small spherical bubble moves upward in a glass of water. The drag force on the bubble can be calculated using Stokes law. So state the condition needed for Stokes law to apply to the bubble. So if you guys flip the question paper, so you guys can see there was other question that is saying whenever we want to apply the Stokes law, this is the question. So if you want to apply the Stokes law, the liquid flow around the ball or the around the moving object, here it is a bubble, so the liquid flow around the bubble must be laminar. So you guys can write that point, the liquid flow around that bubble must be laminar. That will be the condition. So the second one, the bubble moves upward at a constant velocity. So it is moving at a constant velocity. The volume of the bubble is about 5.3 times 10 to the power minus 11 meter cube. Show that the upthrust on the bubble is equal to 5 times 10 to the power minus 7 Newton. So the density is also given. So this is direct substitution. You guys know the equation for upthrust. Upthrust is equal to rho Vg, where V is the volume of the liquid which is displaced. So you can consider a bubble which is moving up in a liquid, then the volume of the bubble is equal to the volume of the liquid displaced. So we can substitute all the values. The density of the water is also given here, 998 times the volume is equal to 5.3 times 10 to the power minus 11 into G is 9.81. So you will get the value for upthrust. So upthrust is also a force, its unit will be equal to Newton. So you guys have to do the calculation to find the upthrust. So it will be a value which is comparable to 5 times 10 to the power minus 7 Newton. 5 times 10 to the power minus 7 Newton. Okay, now the second question, the bubble move upward at a constant velocity. So this is moving upward with a constant velocity. Constant velocity is achieved when the downward forces are balanced by the upward force. What are the downward forces acting here? So the bubble is raising up, right? So when the bubble is raising up, the force acting in the upward direction will be upthrust. So the drag force is always opposing the motion of the liquid drop or anything which is moving through the fluid. So the drag force will be also in the downward direction. And what will be the other force in the downward direction will be the mass, the weight of the bubble. Okay, so these are the forces which are acting in the downward direction, and this is a force which is acting in the upward direction. And while discussing the question, you guys keep in mind, so if we are saying something rising up through a fluid, then the upthrust will be greater than the downward force. The upthrust will be greater than the weight which is acting in the downward direction. Okay, so now we can write the equation. Whenever it is rising up with a constant velocity, then the upward force and the downward force are balanced. So we can write upthrust will be equal to F plus mg. F plus mg. So here they are saying that we can ignore the weight of the bubble. So when you guys are ignoring the weight of the bubble, so you can ignore this term. Then the upthrust must be equal to the force, viscous drag force. So you guys know the equation for viscous drag force, which is 6 pi eta rv, right? 6 pi eta rv. Here the v is velocity, terminal velocity. Okay, now the velocity is given in the question. Velocity is given in the question. We are able to calculate the value of the viscous drag force. But one more thing we have to do, that is the R is not directly given, but we know that the volume of the bubble. So you guys know bubble is spherical in shape, and if its radius is equal to R, then its volume will be given by 4 over 3 pi r cube. So if you rearrange the equation, we get 3 times V over 4 times pi will be equal to r cube. So if I take the cube root of 3 times V over 4 pi, then I will get the value of radius. Then I can substitute that value right here in the equation. So R is known, V is known, viscosity of the water is also given in the question, eta is known. Then we can calculate the value of F. So if the value of F is comparable to the upthrust that we are calculated, the upthrust is 5 times 10 to the power minus 7. If it is comparable with the upthrust, then we can say that the Stokes law can be applied here. If it is not comparable with the viscous torque force is not comparable with the upthrust, then we can say that the Stokes law cannot be applied. So we can't apply Stokes law. Okay, so here the answer is around 1.49 or 1.5 times 10 to the power minus 7, something around that value. But the upthrust is 5 times 10 to the power minus 7. They are not comparable in this case, particular case. So here we can't apply Stokes law. That is the answer for this particular question. So now we can solve the next question. So the scientists are using a weather balloon to carry the equipment into the upper atmosphere to monitor the weather conditions. So this is the balloon shown here. So the photograph shows a weather balloon. So the upthrust act on the balloon and the balloon is released and accelerate upwards. State what is meant by the upthrust. So this is actually a 1 mark question. So you have to write a small definition about upthrust. So you can write this is the upward force. Upthrust is the upward force. This upward force is a result of the upward force which is caused by the displacement of the fluid. So this is enough. Upward force caused by the displacement of the fluid. 1 mark. You will get 1 mark. Okay. So in the next part of the question, when the balloon is released, we are releasing the balloon. So this is initially accelerated in the upward direction with a 4.80 meter per second square. So we know that to accelerate an object, we have to apply a force in that particular direction, right? So if it is accelerated in the upward direction, then there will be a force in the upward direction. And that force will be given by Newton's second law. Force is equal to mass into acceleration. So we can write mass into acceleration here is equal to 4.80 meter per second square. So this is the force in the upward direction. Who is providing this upward force? The upthrust is actually providing the upward force. So what is the equation for upthrust? Upthrust is equal to rho Vg. So this complete upthrust will not be utilized for accelerating it because there is a force in the downward direction which is equal to the weight of the balloon. Okay, now we can write the upward force, mass into acceleration. So you can write mass into acceleration is 4.80, which is equal to upthrust. Upthrust is equal to rho Vg minus weight of the balloon, mg. Okay, we have to find out the value of m. So you guys know m times 4.80 is equal to rho Vg. So what is the value of mg? So you guys, we don't know the value of m, but we know the value of g, which is constant 9.81. So we can take this term to left hand side of the equation. Then we will get m times 4.80 plus 9.81, which is equal to rho Vg. So we can rearrange the equation. Then we get m is equal to rho Vg over 4.80 plus 9.85. Then we are able to find out the value of mass. Okay, if we get the mass, then we can find out the weight of the balloon using the equation mg. Then you guys will get a value which is comparable to 30 Newton. Okay, so that's the answer for the sixth question. Now we are moving to the second part of the sixth question. So here the scientists want to make the measurement at a height 25 kilometer where the balloon would stop rising. Whenever it reaches 25 kilometer, it will stop rising. Stop rising means then the upthrust will be balanced by the weight, so it will float in air right there. Okay, so the balloon will expand as it rises. We know that whenever we are going to higher altitude, then the pressure of air decreases. As a result, the balloon will expand. But the balloon will burst if the volume exceeds 50 meter cube. If that volume exceeds 50 meter cube, then it will burst. So deduce whether the weather balloon could support the equipment at a height of 25 kilometer without bursting. So what we have to do is, we have to find out the value of the volume, and if the volume at 25 kilometer, if the volume is greater than 50 meter cube, then the balloon will burst. But if the volume is less than 50 meter cube, then the balloon can be used to study the weather at 27 kilometers. Clear? Okay, now we have to calculate the volume at 25 kilometer, and we said that the balloon will float when the downward force, which is weight of the balloon, is equal to the upthrust. So then it will float in air. Okay, so you guys already know the weight of the balloon, which is about 30 Newton, right? It's about 30 Newton. So you guys know the equation for upthrust, which is equal to rho Vg. So you can calculate the volume using the equation 30 Newton over rho G. So to find out the density at the height 25 kilometer, you guys can use this graph. That is the use of the graph. So here, this is 25 kilometer. Then you have to draw a line to here. Then you will get the density of air at that particular altitude. So at 25 kilometer, it's about 0.04. So you have to put rho is equal to 0.04 kilogram per meter cube. Then what is acceleration due to gravity? You guys know the value of acceleration due to gravity, which is 9.81. Then you guys will get the value for volume. So if you get the value for volume, if the volume is less than 50 meter cube, then we can use the balloon to find the weather at 25 kilometers altitude. And if the volume is greater than 50 meter cube, then we can't use this balloon because the balloon will burst. Okay, so here in this question, the volume is less than 50, so we can use this weather balloon. You can do the calculation and verify that.